Tonight, we follow the story of the black hole, a silent giant that bends space and time into shapes beyond imagination. Welcome to the Orbit for Sleep channel. Let us follow the orbit of science and drift gently towards sleep as we explore the darkness where gravity reigns and light fades into silence. A black hole is one of the strangest and most powerful phenomena in the universe. It is not a hole in the sense of an empty space, but rather a region where gravity becomes so intense that nothing, not even light, can escape. The idea may sound like science fiction, but black holes are a real consequence of Einstein's theory of general relativity. According to this theory, mass bends the fabric of space and time. When enough mass is packed into a small region, the curvature becomes infinite. That is a black hole. Imagine the universe as a giant sheet of soft fabric. If you place a marble on it, the fabric curves slightly. If you place a heavy ball, it sinks deeper. A black hole is like placing an unimaginably heavy object, so heavy that it rips the fabric downward into a bottomless pit. Once something falls in, it can never return. The edge of this pit, where escape becomes impossible, is called the event horizon. Crossing this boundary means leaving the visible universe forever. Black holes form at the end of a massive star's life. Inside every star, there is a delicate balance between two forces: the outward push from nuclear fusion and the inward pull of gravity. Fusion occurs when atoms of hydrogen are squeezed together to form helium, releasing light and heat. This process creates pressure that keeps the star from collapsing. But when the star runs out of fuel, fusion stops and gravity takes over. The star's core collapses inward, and if the mass is large enough, it continues shrinking until it becomes a singularity, an infinitely dense point surrounded by a curved shell of spacetime. Around many black holes, there is an accretion disk, a glowing ring of gas and dust spiraling inward. As the material falls, it heats up to millions of degrees and emits X-rays. From far away, this radiation is one of the few clues we have that a black hole exists. In some cases, black holes also produce powerful jets that shoot matter and energy thousands of light years into space. These cosmic beams show how something so destructive can also shape galaxies and trigger the birth of new stars. Time itself behaves strangely near a black hole. To a distant observer, a falling object appears to slow down, frozen in time as it approaches the event horizon. But for the object itself, time continues normally until it crosses the boundary, and then it is gone forever. This means that time and space are not separate things near a black hole. They merge into a single curved reality where our usual understanding of distance and duration breaks down. Although we cannot see black holes directly, we have learned to observe their influence. Astronomers have captured images of the glowing rings around supermassive black holes in distant galaxies. These cosmic giants weigh millions or even billions of times more than our Sun and sit at the centers of galaxies, including our own Milky Way. Their gravity organizes the motion of stars, gas, and dust, acting like a cosmic anchor. To study black holes is to look into nature's most extreme laboratory, a place where the laws of physics stretch to their limits. It reminds us that the universe is both elegant and ruthless, ruled by invisible forces that we can barely comprehend. And yet, within that darkness lies a deep kind of order, a quiet reminder that even the most mysterious corners of space follow the same universal laws that shape us all. When a star is born, it begins its life by fusing hydrogen atoms into helium deep within its core. This process, called nuclear fusion, releases enormous amounts of energy that push outward against the inward pull of gravity. The two forces, pressure from fusion and gravitational collapse, exist in perfect balance. For most of a star's life, this balance keeps it stable, shining gently for billions of years. But when the star runs out of hydrogen fuel, the story changes dramatically. When fusion stops, gravity begins to dominate. The outer layers of the star may expand, forming a red supergiant, while the core becomes unstable. If the star is massive enough, typically more than 3 times the mass of our Sun, its own weight crushes the core beyond imagination. Protons and electrons merge into neutrons, and the collapse continues until the density becomes so extreme that nothing can resist it. Space and time fold inward. black hole is born. This transformation happens in a moment of cosmic violence. The outer layers of the dying star explode outward in a supernova, one of the most powerful events in the universe. The blast scatters elements like carbon, oxygen, and iron into space, materials that will later form planets, oceans, and even life itself. But the core that remains collapses inward faster than light can respond. Gravity pulls everything to a single, infinitely dense point, the singularity. Around this singularity forms the event horizon, the invisible boundary where escape becomes impossible. To visualize this, imagine a star as a giant mountain made of light and heat. When its fuel is gone, the mountain caves in on itself, collapsing until it becomes smaller than an atom. The energy once spread across millions of kilometers is now trapped in a volume so tiny that the concept of size no longer makes sense. Inside this boundary, all paths lead inward. No matter how hard light tries to escape, the curved geometry of space bends it back. Not all stars end this way. Smaller stars like our Sun will die more quietly, becoming white dwarfs or neutron stars. Only the most massive stars can collapse into black holes. Yet there are even greater forms, supermassive black holes, which can contain millions or billions of solar masses. Their origin is still a mystery. Some scientists believe they form from the collapse of enormous gas clouds in the early universe. Others think smaller black holes merged over time to grow into giants. When matter falls into a newly formed black hole, it forms a glowing disk around it called an accretion disk. Friction and gravity heat this material until it shines brighter than all the stars in a galaxy. In this violent glow, we glimpse the process of creation through destruction, the death of a star giving birth to a new cosmic phenomenon. Over time, the black hole settles into silence. From the outside, it appears calm, as if nothing is happening. But inside, matter and energy continue their endless fall toward the singularity. Time itself slows near the event horizon, stretching seconds into eternities. For an outside observer, the collapse seems frozen, as though the star's final breath lingers forever. The birth of a black hole is both an ending and a beginning. It marks the death of a star, but also the creation of one of the most fascinating objects in existence. From destruction comes gravity's purest expression, a place where the universe's rules fold into mystery, and light itself must surrender. Inside the event horizon, the rules of the universe begin to twist in ways that challenge all understanding. The event horizon itself is not a physical surface, but an invisible boundary marking the point of no return. Once something crosses it, there is no way back. Light, matter, even time itself, all are drawn inevitably inward, toward the singularity at the heart of the black hole. To imagine what happens beyond that boundary, we must rely on mathematics and theory, because no signal ever escapes to tell us. According to general relativity, the closer you approach the event horizon, the more extreme gravity becomes. Space bends sharply, and time slows down. For an outside observer, anything falling toward the black hole appears to move slower and slower, its light stretched into red until it fades completely. But from the perspective of the falling object, time seems to pass normally. It simply falls inward, crossing the event horizon in an instant, never to return. Inside, gravity overwhelms all known forces. The pull toward the center is so strong that no material object can resist. Atoms are stretched apart, their particles torn from each other in a process known as spaghettification. Imagine falling feet first into a black hole. The difference in gravity between your feet and your head becomes so large that your body would stretch into a long, thin line, like a strand of spaghetti. This is not just a vivid image. It is a real prediction of physics near such intense gravitational fields. As matter falls deeper inside, it spirals toward the singularity, a point where density becomes infinite, and the known laws of physics collapse. At this point, space and time themselves lose meaning. We cannot describe what happens beyond because our equations break down. It is a place where the curvature of space becomes infinite, and time ceases to flow in the way we understand it. Some scientists suggest that the singularity may not truly be a point, but rather a region where quantum effects become dominant. In this view, the universe's smallest building blocks, particles and energy fields, might prevent an infinite collapse. Quantum mechanics could replace the singularity with a finite, but still incredibly dense structure. However, no one knows for sure. Until we have a full theory of quantum gravity, the heart of a black hole remains a mystery. One thing is certain: information that crosses the event horizon seems to vanish. This presents one of the greatest puzzles in modern physics, the black hole information paradox. If information is destroyed, it violates the fundamental laws of quantum mechanics. But if it somehow survives, how is it preserved? Some theories suggest that information may be encoded on the surface of the event horizon itself, like a hologram. Others propose that it may eventually leak out as faint radiation, known as Hawking radiation. These ideas remain under intense study, as they may reveal something profound about the nature of reality itself. Inside a black hole, space and time trade roles. Instead of space describing where you are and time describing when you are, time becomes a direction you cannot avoid, pulling you inward just as inevitably as gravity. The singularity is not a place you can stand upon. It is a moment in time you are destined to reach. No matter which way you move, every path leads forward in time toward the same end. The interior of a black hole, then, is not merely darkness. It is a realm where the universe's rules fold in on themselves. It challenges our understanding of causality, space, and even existence. To fall inside is to cross into a region where reality itself is rewritten, and where the line between science and philosophy begins to blur. Light is the fastest thing in the universe. It travels at about 300,000 kilometers per second, crossing the distance from the Earth to the Moon in just over a second. Yet even light cannot escape the grip of a black hole. This simple truth reveals just how powerful a black hole's gravity truly is. The question of whether light can escape defines the very boundary of a black hole, the event horizon. To understand why light cannot escape, imagine space not as emptiness, but as a flexible fabric. Every massive object, like a planet, a star, or a galaxy, bends this fabric slightly, creating what we call gravity. The more massive the object, the deeper the curve. A black hole bends the fabric so steeply that it becomes a well with walls too steep for light to climb. Once light reaches the event horizon, the slope becomes infinite. The photon, the particle of light, has no path left that leads outward. It can only move inward, forever trapped by space-time itself. This boundary is what makes a black hole truly black. From the outside, it absorbs all incoming light and emits none of its own. New reflection, new glow, new escape. It becomes invisible against the backdrop of space. The only way we can detect it is by observing what happens around it, how nearby matter behaves, how light bends near its edge, and how energy is released as gas and dust spiral inward. Einstein's theory of general relativity explains this behavior through the concept of escape velocity, the speed needed to break free from gravity. On Earth, that speed is about 11 kilometers per second. For a neutron star, it might be half the speed of light. For a black hole, the escape velocity equals the speed of light itself. That means no particle or signal can overcome it. If something falls too close, it cannot resist the pull. Even light, the universe's swiftest traveler, finds no way out. But light does not simply disappear. When light passes near a black hole, it bends dramatically, curving along the distorted geometry of space. This phenomenon is called gravitational lensing. To a distant observer, it can create a glowing ring around the black hole, known as the photon sphere. Here, light orbits the black hole multiple times before eventually being swallowed or scattered away. This glowing ring was famously captured in 2019 by the Event Horizon Telescope, the first real image of a black hole's shadow. What we saw was not the black hole itself, but the light twisted around its edge. If you were to approach a black hole, you would see light behave in impossible ways. The stars behind it would stretch and distort, forming circles around the dark center. The closer you got, the slower time would seem to pass. Eventually, light from the universe outside would fade into darkness, leaving only the void ahead. The black hole would not shine, but it would appear surrounded by a halo of dying light, curved by gravity's final embrace. In a poetic sense, light does not lose its speed, it loses its direction. It continues to move at the same incredible pace, but space itself curves so completely that every possible path bends inward. The light is not destroyed. It is trapped in a world where all roads lead to the center. This idea that even light cannot escape defines the black hole's nature and its mystery. It is the point where the universe itself seems to turn inward, hiding its secrets from view. Yet, paradoxically, by studying how light bends, fades, and vanishes around black holes, we have learned more about space, time, and gravity than ever before. The darkness of a black hole, it seems, is not the absence of light, but the ultimate expression of how light and gravity dance at the edge of the universe. Falling into a black hole is one of the most haunting and fascinating thought experiments in physics. No one has ever experienced it, and no one ever could return to tell the story. Yet, through the lens of science, we can imagine what that journey might be like. It is a descent not only through space, but through time itself, a slow unraveling of reality. Imagine you are floating in the darkness of space, approaching a black hole. At first, everything seems calm. The stars still shine, and the black hole itself looks like a perfectly round void framed by a glowing ring of light, the accretion disk. As you drift closer, that light begins to distort. Space itself curves around you, bending the paths of distant stars into strange arcs. The closer you move, the more the universe behind you stretches and twists, as if you were falling into a cosmic whirlpool. From your point of view, you begin to accelerate, faster and faster, pulled by gravity's irresistible hand. If the black hole is small, you would not survive the trip for long. The gravitational difference between your feet and your head would become enormous. Your body would stretch vertically and compress sideways, a process known as spaghettification. Every atom in your body would be pulled apart, then reduced to streams of particles spiraling inward toward the singularity. But if the black hole is supermassive, millions of times heavier than the sun, your experience would be different. The tidal forces at the event horizon would be weaker, at least initially. You could cross the event horizon without even noticing it. There would be no sudden flash, no wall or edge, just the silent, invisible line of no return. You would keep falling inward, watching the outside universe slow down as your clock continues ticking normally. To distant observers, however, you would appear frozen at the edge, fading slowly as your light stretches into infinity. As you descend deeper, light from the outside universe would fade until darkness surrounds you completely. The flow of time would behave strangely. From your perspective, you would fall in seconds, but to an outside observer, your fall would take forever. Time and space exchange roles. The direction of your fall becomes the direction of time. Every path you take leads inevitably toward the singularity, the dense core at the center. Inside, the laws of physics as we know them no longer apply. The gravitational pull becomes infinite, crushing everything to a point where space and time cease to exist in any familiar sense. We do not know what lies beyond that boundary, whether it is truly an end or perhaps a bridge to another region of the universe. Some theories suggest that the core of a black hole might connect to another point in space through what is called a wormhole, a tunnel through space-time. But this idea remains speculative, beyond the reach of current science. For the falling traveler, there is no pain, no sensation of motion in the final instant. Time slows to nothing. The universe above fades away, and all paths converge to a single, inescapable destination. From the outside, your journey ends at the event horizon. From the inside, it continues into the unknown. Falling into a black hole is not just a physical fall. It is a journey into the limits of existence. It reminds us that the universe holds places where our understanding fails, where the fabric of reality folds back on itself. The black hole is both a destroyer and a teacher, showing us that even the most terrifying depths of space are governed by the same elegant laws that shape the stars, the planets, and life itself. At the very center of a black hole lies the singularity, a point where our understanding of the universe collapses. It is the ultimate edge of knowledge, a place where gravity becomes infinite and the known laws of physics no longer apply. In simple terms, the singularity is what remains when matter is compressed to zero volume and infinite density. It is not a physical object we can observe or measure, but rather a mathematical prediction that signals the breakdown of our current theories. To understand how strange this idea is, imagine taking a mountain and crushing it smaller and smaller. The atoms would lose their structure, the protons and neutrons would collapse, and eventually, everything would be reduced to an infinitely dense point. This is what happens to the core of a massive star when it forms a black hole. Space and time themselves are pulled inward, wrapping around the singularity like a whirlpool that never ends. Einstein's theory of general relativity describes how gravity bends space and time, but it cannot explain what happens at the singularity. The equations predict infinity, an impossible result in nature. This tells us that something deeper is missing from our understanding. Quantum mechanics, the theory that describes the behavior of particles at the smallest scales, must somehow play a role. But when we try to combine relativity and quantum theory, the math breaks down. The singularity is the frontier where these two great pillars of physics collide. Some physicists believe that the singularity may not truly be a point. Instead, it might be a region where quantum effects prevent matter from collapsing completely. One idea, called loop quantum gravity, suggests that space itself has a smallest possible unit, a kind of grain of space-time. If this is true, then the singularity would not be infinite, just unimaginably dense. Another theory proposes that the singularity could bounce, forming a new universe on the other side, a cosmic rebirth hidden inside every black hole. The singularity also raises deep questions about time. Inside a black hole, space and time switch roles. The singularity is not a place you can avoid by moving sideways or backward. It is a moment in time that lies in your future. Once you cross the event horizon, moving toward the singularity is as inevitable as aging. Every second brings you closer to that endpoint, no matter what you do. Because we can never observe the singularity directly, it exists as a concept that challenges both science and philosophy. It represents a limit, a reminder that our most trusted theories may only describe part of reality. Just as the horizon hides what lies beyond the sea, the singularity hides what lies beyond our understanding. In recent years, scientists have used advanced simulations to study what happens near the singularity. They've discovered that the extreme curvature of space may tear apart not only matter, but also information. This leads to one of the greatest mysteries in modern physics. If information truly disappears inside a singularity, does the universe lose part of itself? Or is that information somehow preserved in ways we cannot yet comprehend? The singularity is, in a sense, a mirror of human curiosity. It stands as both a mystery and a challenge. It reminds us that even as our equations describe galaxies and stars, there are still corners of the cosmos where mathematics becomes poetry and knowledge turns into wonder. It is the point where the universe folds into itself, a place beyond physics, beyond light, and perhaps beyond time itself. An accretion disk is one of the brightest, most energetic structures in the universe, and it forms around some of the darkest objects ever known. When gas, dust, and fragments of stars approach a black hole, they do not fall straight in. Instead, they swirl around it, forming a vast, rotating disk. This disk is called an accretion disk, and it behaves like a cosmic whirlpool, beautiful, violent, and incredibly hot. To understand why this happens, imagine trying to drop a stone into a spinning drain. If you release it at the edge, it does not fall straight down. It spirals around and around before it finally disappears. The same thing happens with matter in space. Everything has some amount of angular momentum, a natural tendency to rotate. As matter gets closer to the black hole, that rotation speeds up, just like an ice skater who pulls their arms in to spin faster. Inside the accretion disk, the forces are extreme. The matter in the disk moves at enormous speeds, sometimes up to half the speed of light. Friction between particles heats the disk to millions of degrees. At those temperatures, gas glows brightly, releasing X-rays and gamma rays. These high-energy signals are some of the strongest indicators that a black hole is nearby. We cannot see the black hole itself, but the glowing disk surrounding it becomes a beacon in the darkness. The disk is not smooth or calm. Turbulence flows through it, like storm currents in an ocean. Shock waves ripple through the gas. Magnetic fields twist and wrap around the moving material, creating chaotic patterns that constantly change. Some parts of the disk clump together, forming temporary structures before being torn apart again. This constant motion creates enormous energy, enough to power some of the brightest objects in the universe. In the inner regions of the disk, gravity becomes even more intense. The material is pulled inward, losing energy as it spirals closer to the event horizon. This region is known as the innermost stable circular orbit, or ISCO. Beyond this point, no orbit can remain stable. Anything crossing that threshold plunges directly into the black hole. Accretion disks also give birth to another remarkable phenomenon: relativistic jets. These are narrow beams of particles and energy that shoot out from the poles of a black hole at nearly the speed of light. Scientists believe that magnetic fields in the accretion disk twist and accelerate particles, launching them far into space. These jets can extend thousands or even millions of light years, lighting up entire galaxies. They are so powerful that they can shape the formation of stars and influence the evolution of galaxies. From a distance, the accretion disk looks like a glowing halo around a circle of darkness. The light emitted from it is distorted by the black hole's gravity, bending around the event horizon. This creates a bright ring, an illusion of light that appears to encircle the void. In 2019, scientists captured an image of such a ring for the first time using the Event Horizon Telescope. It was the shadow of a black hole, outlined by the light of its accretion disk, a direct glimpse into one of nature's most extreme environments. Despite its violence, the accretion disk is a natural part of cosmic evolution. It recycles matter, distributing energy and influencing the structures around it. Stars can form from the materials that swirl in these cosmic whirlpools, and galaxies can be shaped by the jets they produce. The accretion disk is a bridge between creation and destruction, where matter is broken apart, heated, transformed, and eventually consumed. In the heart of darkness, the accretion disk becomes a lantern. It shines with the energy of a dying star, revealing the hidden presence of the black hole. Through its light, we observe the physics of extreme gravity, the behavior of matter at incredible speeds, and the beautiful chaos that surrounds the universe's most mysterious objects. Spaghettification is one of the most dramatic and unsettling effects predicted by physics near a black hole. The word may sound whimsical, even humorous, but what it describes is anything but gentle. It refers to the extreme stretching of objects as they fall into a strong gravitational field. Under the influence of a black hole, matter is pulled apart lengthwise and compressed sideways, turning even the most solid object into a long, thin stream. like a strand of spaghetti. To understand why this happens, imagine you are falling feet first toward a black hole. Gravity grows stronger the closer you are to the center. Your feet, being closer, feel a stronger gravitational pull than your head. This difference in force is called a tidal force. On Earth, tidal forces from the moon simply move the oceans, creating tides. Near a black hole, however, these forces are so extreme that they stretch your entire body. At first, the difference in gravity is small. You would not feel anything unusual. But as you fall deeper, the gravitational gradient, the change in gravity over distance, becomes sharper. Within a very short distance, gravity pulling on your feet becomes much stronger than gravity pulling on your torso or head. Your body would begin to elongate. Bones, muscles, and tissues would stretch, losing their structure. At the same time, the sides of your body would be squeezed inward, collapsing your width, even as your height increases. This effect is not limited to humans. Stars, planets, asteroids, everything that crosses the event horizon is subjected to the same fate. A star that wanders too close to a black hole can be torn apart in a tidal disruption event. Its material stretches into long streams of hot gas that wrap around the black hole before being consumed. Observatories on Earth and in space have recorded flashes of light from these events, watching stars shredded by invisible forces. The physics behind spaghettification comes from general relativity. In curved space-time, the path of falling objects is not straight, but follows the geometry of the gravitational field. As you get closer to the singularity, space-time becomes extremely curved. The inward pull grows infinitely strong, and the bending of space itself forces matter into a narrow path. Nothing, not even the structure of atoms, can withstand this pressure. For smaller black holes, those with similar mass to the Sun, the tidal forces at the event horizon are deadly. You would be torn apart long before crossing the boundary of no return. But for supermassive black holes, the event horizon is so far from the singularity that tidal forces there are relatively weak. You could cross the event horizon intact, only to encounter spaghettification deeper inside. This strange distinction means that the size of the black hole determines how and when spaghettification occurs. Inside the event horizon, spaghettification becomes unavoidable. The singularity acts like a gravitational funnel, pulling matter inward along a single direction. Every point in space leads toward the same destination. Time itself becomes aligned with this inward motion, meaning you cannot slow or stop your journey. You stretch, compress, and finally disintegrate, transformed into streams of particles rushing toward the center. Even though spaghettification is terrifying, it reveals the power and beauty of gravity. It demonstrates how space-time can shape matter, how forces we barely feel on Earth can become overwhelming in the depths of the universe. It is a reminder that gravity is not just a pull, it is the curvature of space itself. In the end, spaghettification is not simply destruction. It is part of the natural cycle of the cosmos. The matter stretched and torn becomes part of the black hole's environment, adding to the accretion disk, feeding jets, and influencing the evolution of galaxies. Through this violent transformation, the universe recycles matter, shaping the stars and worlds that will one day form again. Hawking radiation is one of the most surprising and profound ideas in modern physics. It suggests that black holes, which are known for swallowing everything that comes near them, might actually lose energy and shrink over time. This process, called black hole evaporation, challenges long-held beliefs and shows that even the darkest objects in the cosmos are not eternal. To understand Hawking radiation, we start with the strange behavior of empty space. According to quantum mechanics, the universe is never truly empty. Even in a perfect vacuum, tiny pairs of particles and antiparticles briefly appear, then disappear. These pairs are called virtual particles. They exist for only a fraction of a second, but they constantly flicker in and out of existence everywhere in space, including near the event horizon of a black hole. When a pair of virtual particles forms near the event horizon, something unusual can happen. Normally, the particle and antiparticle quickly find each other and annihilate, disappearing as fast as they appeared. But if they form in just the right spot, one of the particles can fall into the black hole, while the other escapes into space. To an outside observer, this escaping particle appears as real radiation coming from the black hole. The particle that falls in carries negative energy, which reduces the black hole's total mass. Over incredibly long periods of time, this slow leakage of energy causes the black hole to shrink. This is what we call evaporation. It is not a fast process. A black hole with the mass of the sun would take far longer than the age of the universe to evaporate completely. But tiny black holes, if they exist, would evaporate much faster, possibly ending in a brilliant final burst of energy. Hawking radiation arises from a combination of two great theories: quantum mechanics and general relativity. Quantum mechanics describes how particles behave at very small scales. General relativity describes how gravity shapes the universe. When these two meet at the edge of a black hole, they create a phenomenon that neither theory alone could predict. Stephen Hawking first proposed this idea in 1974. At first, even he doubted it. But as the mathematics became clearer, it revealed a deeper truth about the connection between gravity, temperature, and information. One of the most surprising results is that black holes have a temperature. The smaller the black hole, the hotter it becomes. A large, supermassive black hole emits almost no Hawking radiation. It is extremely cold. A tiny black hole, however, would glow intensely. This temperature is not something we can feel or touch, but it is encoded in the radiation escaping from the event horizon. Hawking radiation also connects to the information paradox, the question of what happens to the information about everything that falls into a black hole. If a black hole evaporates completely, where does that information go? Does it disappear forever, breaking the rules of quantum physics? Or is it somehow preserved in the radiation that escapes? Physicists are still trying to solve this mystery. Some theories suggest that information may be encoded in subtle patterns within the radiation itself. Others propose that the event horizon acts like a hologram, storing information on its surface. Although we have not yet observed Hawking radiation directly, it is far too faint for current instruments. The idea has reshaped our understanding of black holes. It tells us that black holes are not simple cosmic traps, but dynamic objects that interact with the universe. They absorb, radiate, evolve, and eventually fade. In the long-term future of the universe, Hawking radiation may determine the final fate of everything. Billion by billion years into the cosmic future, stars will die, galaxies will drift apart, and even the largest structures will lose their energy. In the end, only black holes will remain. they will fade slowly, releasing the last traces of energy back into the universe. When the final black hole evaporates, the cosmos will fall silent, filled only with faint radiation and darkness. In this quiet ending, Hawking radiation becomes the universe's final whisper, a reminder that nothing, not even a black hole, lasts forever. Binary black holes are pairs of black holes locked together in a gravitational dance. They orbit a common center of mass, spiraling closer, step by step as they lose energy. This cosmic dance unfolds slowly over millions or even billions of years, driven by the invisible pull of gravity. Although we cannot see the black holes directly, their movement creates one of the most extraordinary phenomena in the universe: gravitational waves. To understand this dance, picture two whirlpools in a vast, dark ocean. Each whirlpool spins, and each affects the movement of the other. As they draw closer, the water around them churns and ripples outward. In space, those ripples are not made of water, they are made of space-time itself. Gravitational waves are ripples in the fabric of the universe, caused by massive objects accelerating. And binary black hole mergers produce some of the strongest waves ever detected. The physics behind this begins with Einstein's general relativity. According to his theory, massive objects bend space and time, and when they move, this curvature changes. That change travels outward at the speed of light, carrying energy with it. For two black holes orbiting each other, their movement distorts space-time again and again, sending a steady rhythm of gravitational waves across the cosmos. As they lose energy through these waves, they spiral closer together. Over time, the orbit tightens. The black holes spin faster and faster, like skaters pulling in their arms while rotating. The closer they come, the stronger the gravitational waves become. This process continues until the final moments, when the black holes merge. In the last fraction of a second, they release more energy than all the stars in a galaxy combined, but not as light, only as gravitational waves. Imagine these waves spreading across space. They stretch and squeeze the very structure of reality as they pass. If they travel through Earth, they change distances by far less than the width of a proton. And yet, with incredibly sensitive instruments, scientists have detected them. In 2015, the LIGO Observatory recorded the first direct evidence of gravitational waves, a slight vibration caused by two black holes colliding more than 1 billion light-years away. This discovery confirmed a major prediction of Einstein's theory and opened a new way of observing the universe. Instead of using light, which black holes absorb, scientists could now listen to the universe through the echoes of gravity. The signals from merging black holes sound like faint chirps rising in pitch as the black holes spiral together. Each chirp tells a story about the size, mass, and energy of the objects involved. Binary black hole mergers are not rare. The universe is vast, and stars often form in pairs. When two massive stars die, each can collapse into a black hole. If they remain close, gravity binds them together. Their orbits may decay slowly over billions of years, but eventually they meet in a moment of cosmic violence. Each collision creates a new, larger black hole, a single object where two once existed. This process shapes galaxies. The powerful gravitational waves released during these mergers carry energy away, influencing the motion of stars and gas around them. In the centers of galaxies, Supermassive black holes may merge as entire galaxies collide. These enormous events send gravitational waves so massive that future observatories in space, like LISA, may detect them. The dance of binary black holes also raises deep questions. What happens to the information stored in the two original black holes? Does their combined singularity hold the memory of everything that fell into them, or is it forever lost? And what does the final merged black hole look like inside? These are mysteries science is still trying to solve. Seen from a distance, binary black holes are silent, invisible dancers, yet through their movement, they shake the entire universe. Gravitational waves are the music of this dance, soft, steady, and ancient. They remind us that even in the deepest darkness, the universe is full of motion, rhythm, and hidden energy. At the center of almost every large galaxy, including our own Milky Way, there lies a supermassive black hole. These giants are millions to billions of times the mass of the Sun, yet they sit in silence, hidden behind spiraling clouds of stars and dust. Their presence is not obvious at first glance. They emit no light, no heat, and no signal that our eyes can detect. But their gravitational influence shapes entire galaxies, guiding the motion of stars and sculpting the structure of cosmic systems. A galaxy is not a simple collection of stars. It is a complex, rotating disk of gas, dust, dark matter, and star clusters, all orbiting a common center of mass. At the heart of this swirling structure rests the supermassive black hole, a gravitational anchor. Just as a spinning wheel needs a stable hub, a galaxy's rotation is shaped by this central mass. Gravity binds the stars to their paths, preventing them from flying away into intergalactic space. To understand how we know these massive objects exist, scientists observe how stars move near the galactic center. In the Milky Way, astronomers have tracked stars in orbit around a seemingly empty spot. These stars move at incredible speeds, faster than anything in our solar system. One star, named S2, orbits the center every 16 years, reaching speeds of over 7,000 kilometers per second. Nothing visible lies at the center of its orbit. The only explanation is a supermassive black hole, known as Sagittarius A*, containing about 4 million times the mass of the Sun. The presence of black holes at galactic centers raises an intriguing question. Which came first, the galaxy or the black hole? Some theories suggest that supermassive black holes formed early in the universe, acting as seeds around which galaxies grew. Others propose that galaxies formed first, and their central regions collapsed over time to create black holes. Observations show both patterns. Some galaxies have black holes so large that their growth seems to outpace the formation of stars. In others, black holes appear to grow slowly by feeding on surrounding gas and merging with other black holes. Although supermassive black holes dominate the center of galaxies, they do not act like cosmic vacuum cleaners. Their gravitational pull extends only so far. Stars far from the center feel only a gentle tug, not a threat. Most stars in a galaxy orbit peacefully, unaffected by the black hole itself. It is only the material that strays too close, gas clouds, dust, and unlucky stars, that becomes trapped and shredded. When matter falls toward a supermassive black hole, it forms an accretion disk much larger than those around smaller black holes. The disk glows brightly, emitting intense radiation that can shine across billions of light years. Such powerful black holes are called quasars. In the early universe, quasars were among the brightest objects ever observed, outshining entire galaxies. Their light traveled billions of years to reach Earth, giving us a glimpse into cosmic history. Despite their destructive reputation, supermassive black holes also play a creative role. Their energy output influences how galaxies evolve. When they release powerful jets of particles, these jets can heat surrounding gas, preventing it from collapsing to form new stars. In other cases, the jets compress clouds of gas, triggering bursts of star formation. In this way, black holes act as regulators, controlling the rhythm of growth within a galaxy. The relationship between a galaxy and its central black hole is a delicate balance. The mass of the black hole is strongly correlated with the mass of the galaxy's central bulge. This suggests that black holes and galaxies grow together, locked in a kind of cosmic partnership. When the black hole consumes too much gas, star formation slows. When the galaxy gathers more material, the black hole gains fuel. At the deepest level, black holes at the heart of galaxies remind us that the universe is shaped by forces, both visible and invisible. We see the light of billions of stars, but the true power lies at the center in the unseen gravity that holds everything together. Supermassive black holes may be silent, but their influence echoes through the structure of galaxies, guiding the cosmic dance of stars for billions of years. Black holes are often imagined as silent destroyers, swallowing everything that comes too close. But in the grand story of galactic evolution, they are not only destroyers, they are architects. Supermassive black holes shape the growth, structure, and long-term behavior of galaxies. Their gravity, energy output, and interactions with surrounding gas influence how stars are born, how they die, and how galaxies evolve over billions of years. To understand their role, imagine a galaxy as a living organism. Stars are its cells, gas clouds are its nutrients, and the central black hole is its beating heart. The heart does not control every action, but its rhythm affects the entire system. In the same way, a supermassive black hole does not control each star, but its influence guides the galaxy's history. One of the most important ways black holes shape galaxies is through feedback. Feedback refers to the energy a black hole releases into its surroundings. When a black hole feeds on nearby gas, it generates enormous heat and radiation. Jets of particles shoot outward at nearly the speed of light. These jets push against surrounding gas clouds, heating them and preventing them from collapsing under their own gravity. Since star formation requires cold, dense gas, this heating slows the creation of new stars. In some galaxies, this process is so powerful that star formation stops almost completely. These galaxies become quiet and inactive, filled with old stars but unable to produce new ones. Astronomers call this quenching. Without black hole feedback, galaxies might grow uncontrollably, creating stars too rapidly and exhausting their gas supply. Instead, black holes regulate the pace of growth, acting like cosmic thermostats. But black holes can also encourage star formation. When powerful jets crash into gas clouds, they compress them, triggering bursts of star birth. This is known as positive feedback. In some regions of the universe, black hole jets create waves of star formation that ripple outward through galaxies, lighting them up with new stars. The balance between heating and compression determines whether a galaxy experiences rapid growth or quiet decline. The mass of a galaxy's central black hole is closely linked to the mass of its central bulge, the densely packed region of stars near the center. This connection suggests that black holes and galaxies evolve together. As a galaxy gains more material, its black hole receives more fuel. As the black hole grows, its energy output increases, influencing the surrounding gas. This co-evolution is a slow, delicate dance that unfolds over billions of years. During the early universe, black holes played an especially dramatic role. Quasars, extremely bright, active black holes, shone with incredible intensity. Their radiation illuminated the young cosmos and shaped the distribution of gas across enormous distances. Some quasars were so powerful that they are still visible today, their ancient light crossing the universe to reach Earth. Galaxy mergers also reveal the importance of black holes. When two galaxies collide, their stars pass through one another like ghosts, but their central black holes spiral toward a meeting point. As they merge, they stir up gas, trigger waves of star formation, and reshape the galaxy's structure. Eventually, the two black holes collide and become one, releasing a storm of gravitational waves. The newly formed black hole then settles at the center of the merged galaxy, ready to guide its evolution. The long-term fate of galaxies is intertwined with the behavior of their central black holes. A hungry black hole can halt star formation and change a vibrant galaxy into a calm red one. A quiet black hole allows gas to cool, giving birth to new stars. This balance of feeding and resting determines how galaxies look, how they grow, and how long they shine. In the cosmic timeline, black holes are not passive observers. They are engines of transformation, sculpting galaxies with invisible hands. They regulate the flow of energy, control the birth of stars, and influence the shape of cosmic structures. Their presence teaches us that in the universe, creation and destruction are not opposites, but partners, woven together by gravity, time, and the silent rhythm of the black hole at the galaxy's core. At the heart of our Milky Way lies one of the most extraordinary objects known to science, a supermassive black hole named Sagittarius A*. It is a silent giant, hidden behind clouds of dust and stars, sitting 26,000 light-years away from Earth. Though invisible, its presence shapes the motion of everything in our galaxy's central region. Sagittarius A* is the gravitational anchor of the Milky Way, a massive object around which stars orbit in spectacular cosmic choreography. Sagittarius A* has a massive about 4 million suns, yet for such a massive object, it is surprisingly compact. Its event horizon is roughly the size of the orbit of Mercury. Imagine compressing millions of suns into a region smaller than our solar system. That is the extreme density of this black hole. And while it has an enormous impact on its surroundings, it remains quiet most of the time, unlike active black holes that emit bright jets or glowing accretion disks. Our understanding of Sagittarius A* comes from decades of observations. Astronomers used infrared telescopes to peer through the dust clouds that block visible light. They watched stars in the galactic center orbit something unseen. One star, S2, became famous for its fast, elliptical orbit. It circles Sagittarius A* every 16 years, reaching astonishing speeds over 7,000 kilometers per second. No ordinary object could cause such motion. The only explanation is an invisible, compact mass with immense gravity. These observations provided strong evidence that Sagittarius A times is indeed a supermassive black hole. But the most dramatic confirmation came in 2022, when the Event Horizon Telescope collaboration released the first direct image of Sagittarius A*. The image showed a glowing ring of gas swirling around a dark shadow of the black hole's silhouette. This was not a photograph in the traditional sense, but a reconstruction based on radio waves collected by telescopes around the world. It offered a glimpse into the cosmic depths of our galaxy's center. Although Sagittarius A times is massive, it is relatively calm. It consumes very little material compared to more active black holes in distant galaxies. Occasionally, it flares, brightening slightly as gas falls into it, but most of the time, it remains dormant. This quiet nature is fortunate for life in the Milky Way. If Sagittarius A times were a quasar blasting intense radiation, it could disrupt star formation or even strip away atmospheres from planets. The black hole's influence reaches far beyond its immediate surroundings. It helps maintain the structure of our galaxy. Stars near the center orbit Sagittarius A times in a tight cluster, while stars farther out follow larger paths. This gravitational organization helps stabilize the galaxy's inner regions. In a sense, Sagittarius A times acts as the galaxy's central anchor, providing a focal point for the motion of stars. Over billions of years, Sagittarius A times has likely grown through mergers and by consuming gas clouds and smaller black holes. When galaxies collide, a process that happens often on cosmic timescales, their central black holes spiral toward each other and eventually merge. Sagittarius A times may be the product of such ancient encounters, carrying a record of the Milky Way's history hidden within its mass. Scientists study Sagittarius A times not only to understand our galaxy, but also to test the laws of physics. The extreme gravity near it allows researchers to observe how light bends and how time slows. Data from stars orbiting Sagittarius A times has already confirmed key predictions of Einstein's theory of general relativity. As observational technology improves, we may learn even more about how matter behaves near a supermassive black hole and whether quantum physics plays a role at the event horizon. Sagittarius A times is more than a mysterious object. It is the heart of our galaxy's story, a silent guardian shaping the Milky Way from its center. Though we cannot see it with our eyes, its presence is written in the paths of stars, the rhythm of cosmic motion, and the history of our home in the universe. Black holes are more than astronomical curiosities. They are laboratories for understanding gravity in its most extreme form. Gravity is the force that shapes planets, stars, and galaxies, yet its true nature becomes clearest when pushed to its limits. Black holes stretch gravity to a degree that no other object in the universe can match, offering scientists rare opportunities to test the predictions of physics. To understand why black holes reveal so much about gravity, we start with Einstein's theory of general relativity. Einstein proposed that gravity is not a force in the traditional sense, but the curvature of space-time. Massive objects bend the fabric of space and time, and smaller objects follow the curves created by that mass. A black hole is where this curvature becomes extreme, pulling everything inward in a deep gravitational well. Near a black hole, space-time is stretched, twisted, and bent so sharply that even light cannot escape. One of the most important ways black holes help us understand gravity is through their effect on time. As you approach a black hole, time slows down relative to an observer far away. This effect, called time dilation, has been measured with extraordinary precision. The orbits of stars around Sagittarius A*, the supermassive black hole in the Milky Way, provide evidence for this slowing of time. When these stars reach the closest point in their orbits, their light shifts slightly, matching Einstein's predictions perfectly. Black holes also help us observe gravitational redshift, the stretching of light as it climbs out of a deep gravitational well. Light emitted from material near a black hole loses energy on its way out, shifting to longer wavelengths. This change is not a trick of perspective, but a measurable physical effect, proving that gravity influences not only motion, but also the passage of light. Another remarkable way black holes reveal the nature of gravity is through gravitational lensing, the bending of light around massive objects. When light from distant stars or galaxies passes near a black hole, it curves around the object, creating arcs or rings of distorted images. Astronomers use this bending to map invisible structures, even detecting galaxies that would be hidden behind others. The first images of black hole shadows, captured by the Event Horizon Telescope, were possible because gravity bends light around the black hole's edge, forming a bright halo around a dark center. Perhaps the most groundbreaking evidence for gravity's power comes from gravitational waves. These ripples in space-time, produced by merging black holes, confirm a prediction Einstein made more than a century ago. When two black holes spiral toward each other and collide, the violent acceleration sends waves of curvature across the universe. In 2015, scientists detected these waves for the first time, proving that space-time behaves like a flexible fabric capable of carrying energy. Black holes also expose the limits of our current understanding of gravity. At the singularity, the point at the center of a black hole, gravity becomes infinite. Einstein's equations break down, unable to describe what happens there. This breakdown suggests that general relativity is incomplete. To fully understand gravity, we must reconcile it with quantum mechanics, the theory governing the smallest particles. Black holes are the crucible where these two great theories meet, revealing their contradictions. By studying black holes, scientists hope to uncover clues about quantum gravity, a unified theory that explains both cosmic scale and microscopic forces. The information paradox, which questions whether information swallowed by a black hole is truly lost, points to a deeper connection between gravity, information, and quantum physics. Hawking radiation, which predicts black hole evaporation, further pushes our understanding of gravity into quantum territory. Black holes teach us that gravity is not simple or uniform. It is dynamic, powerful, and deeply connected to the structure of time and space. In the curved space-time around a black hole, gravity becomes visible, no longer an abstract force, but a tangible distortion of reality. By observing these cosmic giants, we learn not only how the universe works, but also how its most fundamental laws unfold at the edge of possibility. The human quest to see the invisible is one of the most persistent and courageous pursuits in science. black holes, being the ultimate hidden objects, represent the greatest challenge of all. They emit no light, reflect no radiation, and reveal nothing directly to our eyes. Yet humanity has spent decades trying to uncover their presence, decode their behavior, and visualize their impact on the universe. In doing so, we have discovered new ways of observing reality, methods that stretch beyond ordinary sight. This quest began long before we understood what a black hole truly was. In the early 20th century, scientists noticed stars behaving strangely, orbiting unseen masses. These motions hinted at hidden gravitational forces. Astronomers realized that something massive and invisible must be shaping these orbits. But because black holes produce no light, they could not be observed the way planets or stars are. So scientists searched for indirect evidence. They looked for the effects of black holes on nearby matter, the way they pull gas inward, the heat produced in their accretion disks, and the radiation emitted before material disappears beyond the event horizon. X-ray telescopes became essential tools for this search. These telescopes detect high-energy radiation invisible to human eyes. When orbiting gas around a black hole becomes incredibly hot, it emits X-rays, which reveal the presence of something hidden. This approach allowed scientists to find many black hole candidates, but they wanted more. They wanted a direct way to see a black hole. That dream seemed impossible until the concept of gravitational lensing emerged. According to Einstein's theory of general relativity, a black hole could bend light around itself, acting like a cosmic magnifying glass. This bending could form distorted arcs or halos, showing us where the black hole sits. In time, this phenomenon became a powerful observational tool, allowing astronomers to detect black holes that would otherwise remain invisible. But humanity's determination did not stop there. Our desire to see the invisible pushed us to build instruments of unprecedented precision. The Event Horizon Telescope, EHT, a global network of radio observatories, was created to capture light circling the edge of a black hole. Instead of using one telescope, scientists coordinated multiple telescopes across different continents, combining their signals through a method called interferometry. This created a virtual telescope the size of Earth. In 2019, the EHT achieved what had once seemed impossible: the first direct image of a black hole's shadow. It was not a photograph of the black hole itself, but of its silhouette, outlined by the glowing gas of the accretion disk. A bright ring encircled a perfect darkness, the event horizon's shadow. The image became an instant symbol of human curiosity and technological achievement. For the first time, we saw the invisible. 3 years later, the EHT made history again by releasing the first image of Sagittarius A*, the supermassive black hole at the center of our Milky Way. This task was even harder because Sagittarius A times changes rapidly. Its bright ring flickers like a flame in the wind. Yet even with these challenges, the image emerged, revealing the hidden heart of our galaxy. The quest to see black holes has also driven advances in gravitational wave science. When LIGO detected gravitational waves from merging black holes in 2015, it opened an entirely new way of observing the universe, listening to its gravitational whispers rather than seeing its light. This innovation proved that black holes can be detected not only through their influence on matter, but through the ripples they send across space-time. The human search for the invisible continues. Scientists are building more sensitive telescopes, developing quantum-based detectors, and refining simulations that reveal the inner workings of black holes. Every success brings new questions, reminding us that the universe hides its greatest secrets behind shadows, distortions, and silence. In the end, the quest to see black holes is not just scientific, it is deeply human. It reflects our need to explore the unknown, to push beyond the limits of vision and understanding. In chasing the invisible, we confront the mysteries of existence itself, proving again and again that curiosity is one of the most powerful forces in the universe. Will black holes eventually disappear? The question reaches far beyond the lifetime of stars or galaxies. It takes us into the distant future of the universe, trillions upon trillions of years ahead. To explore it, we must examine not only the nature of black holes, but the ultimate fate of the cosmos itself. For much of scientific history, black holes were believed to be eternal. Because nothing could escape them, not light, not matter, they were thought to simply grow larger over time by absorbing anything that wandered too close. Larger and heavier, they would persist forever. But this view changed dramatically when Stephen Hawking proposed a new idea. Black holes are not completely black. They emit a faint glow known as Hawking radiation, and through this slow leakage of energy, they can eventually evaporate. Hawking radiation is incredibly weak for large black holes. A black hole the mass of the Sun would take far longer than the current age of the universe to shrink even slightly. A supermassive black hole, like the one at the center of the Milky Way, would require a timescale so vast that it defies comprehension on the order of 10, 100 years or more. This is a number so large that it dwarfs the lifespan of stars and galaxies. It stretches into a cosmic future where the universe is cold, dark, and nearly empty. But eventually, according to theory, even the largest black holes will begin to shrink. As the universe ages, stars will burn out, galaxies will drift apart, and space will expand toward emptiness. Black holes will remain as the final luminous objects, still dark in appearance, but glowing faintly through Hawking radiation. Their glow is not bright, but it represents the slow release of energy, photon by photon, as the black hole loses mass. In their last stages, black holes behave very differently. As they shrink, they heat up. Hawking showed that smaller black holes are hotter. A supermassive black hole is colder than the cosmic microwave background. But when the universe becomes colder than the black hole itself, the black hole will begin to lose energy faster than it gains it. It will slowly warm, radiating more and more. When a black hole becomes extremely small, perhaps the size of a mountain, then a pebble, then a grain of sand, it grows incredibly hot. Its radiation becomes intense. In the final moments of its life, it releases a powerful burst of energy before disappearing completely. This burst would be the black hole's last breath, an explosion of radiation marking the end of an object that once shaped galaxies. This theoretical ending raises profound questions about information. If a black hole evaporates entirely, what happens to the information of everything that fell inside it? Quantum mechanics states that information cannot be destroyed. But if a black hole disappears, where does the information go? Does it emerge with Hawking radiation, encoded in subtle patterns? Does it remain stored somehow in the fabric of space-time? Or does it violate the rules of physics as we know them? The debate continues. There are other ideas too. Some physicists suggest that black holes might leave behind a stable remnant, a tiny object that cannot evaporate completely. Others propose that the universe might be cyclic, meaning that black holes, or their remnants, could play roles in future cosmic rebirths. But the simplest interpretation of current theories is that black holes will not last forever. They will slowly fade, shrinking, heating, and eventually vanishing into a universe that has grown silent. Their disappearance marks the end of structure, the end of energy, and the beginning of what physicists call the heat death of the universe, a time when all processes stop and entropy reaches its maximum. So, will black holes disappear? Yes, eventually, but on timescales so vast that the human mind can barely grasp them. They will be among the last survivors of the universe, fading slowly into darkness, leaving behind only faint radiation as evidence they once existed. Their long, slow evaporation is the universe's final act, closing a story written across billions of years, ending in quiet emptiness. The information paradox is one of the most profound puzzles in modern physics. It sits at the crossroads of two foundational theories, quantum mechanics and general relativity, and exposes their deepest conflict. The paradox asks a simple yet unsettling question. When something falls into a black hole, what happens to the information that describes it? Does it disappear forever, or is it somehow preserved? The nature of reality itself depends on the answer. To understand why this question matters, we must first define what physicists mean by information. In quantum mechanics, information is not just data, it is the complete description of the state of a system. Every particle has properties such as position, spin, momentum, and energy. These properties are never lost. Even if matter changes form, quantum mechanics says information must always remain intact. This principle, known as unitarity, is one of the pillars of modern physics. But black holes complicate this. When matter falls into a black hole, it disappears beyond the event horizon. We cannot observe it. We cannot measure it. The matter seems to vanish from the universe. According to classical relativity, everything that crosses the horizon becomes part of the singularity, a point of infinite density. At that point, information is destroyed. This violates quantum mechanics. This conflict creates the information paradox. Stephen Hawking brought the paradox into sharp focus when he showed that black holes emit Hawking radiation. This radiation, created by quantum effects near the event horizon, slowly evaporates the black hole. If the black hole eventually disappears, what happens to the information inside it? If the information is lost forever, then quantum mechanics fails. If it is preserved, then general relativity's picture of the singularity must be incomplete. For decades, physicists have struggled with this contradiction. One possible solution suggests that information leaks out in Hawking radiation. But Hawking radiation is thermal. It contains no information about what fell in. It is like steam rising from boiling water. It tells you nothing about what ingredients were in the pot. If the radiation is purely thermal, it cannot carry information. Another idea proposes that information is stored at the event horizon. This leads to the holographic principle, the idea that everything inside a region of space can be encoded on its boundary. According to this view, the three-dimensional interior of the black hole is represented on its two-dimensional surface. This challenges our understanding of space. but offers a way to preserve information. A more radical possibility is that black hole interiors and Hawking radiation are connected through quantum entanglement, a phenomenon where particles share information instantly, no matter how far apart they are. Some theories suggest that the information inside the black hole becomes encoded in the radiation through deep, subtle correlations. In 2012, however, a new twist emerged: the firewall paradox. This idea argues that if information is preserved, then the event horizon is not smooth. Instead, it becomes a wall of intense energy, a firewall that destroys anything crossing it. This solution keeps quantum mechanics intact, but breaks general relativity, which says falling into a black hole should be uneventful at the horizon. Each solution creates its own contradiction. Save quantum mechanics, break relativity. Save relativity, break quantum mechanics, or break both and start over. This tension reveals a deeper truth. Our current theories cannot fully describe the universe at the intersection of gravity and quantum physics. The information paradox exposes the cracks in our models, showing us that a deeper, unified theory of quantum gravity is needed. Despite the confusion, the paradox offers philosophical insight. It suggests that reality may not be as solid as it seems. Information, space, and time might be woven together in ways that defy intuition. Reality may be holographic, entangled, or fundamentally different from how we experience it. In the end, the information paradox is not just about black holes. It is about the limits of human knowledge. It forces us to confront the boundaries of our theories and to imagine new possibilities. The universe keeps its secrets tightly locked, but each paradox is a keyhole, hinting at a deeper truth waiting on the other side. Could black holes be portals to other universes? The idea sounds like something from science fiction, yet it arises naturally from the equations that describe black holes. When we push general relativity to its limits, strange possibilities emerge: wormholes, bridges, and alternate regions of space-time that we cannot access from our own universe. Whether these ideas represent physical reality or mathematical imagination remains unknown, but they invite us to explore one of the most fascinating questions in cosmology. To understand the concept, we begin with Einstein's field equations. These equations describe the curvature of space-time caused by mass and energy. In 1916, physicist Karl Schwarzschild found the first exact solution to these equations, a description of a non-spinning black hole. Later, in 1935, Einstein and Nathan Rosen discovered that this solution hinted at a bridge, now called the Einstein-Rosen bridge, connecting two different regions of space-time. This bridge is what we now call a wormhole. The idea is simple in theory, but complex in reality. Instead of a black hole having only an interior leading to a singularity, it might contain a tunnel that opens into another part of the universe, or even another universe entirely. If such a tunnel existed, it might offer a shortcut through space-time, bypassing the vast distances that normally separate cosmic regions. But there is a problem. The original Einstein-Rosen bridge is unstable. It collapses instantly, faster than light can travel through it. Anything attempting to pass through would be crushed before crossing to the other side. Later work showed that stabilizing a wormhole requires exotic matter material with negative energy density, something that has never been observed in nature. Without this exotic matter, The wormhole pinches shut the moment it forms. Despite this instability, the idea of black holes as portals remains compelling. Quantum mechanics adds new layers of possibility. Some theories suggest that at the smallest scales, space-time itself, they fluctuate, creating tiny, short-lived wormholes known as quantum foam. If black holes interact with this foam, they might open pathways to alternate regions of space-time. There is also the concept of white holes, the theoretical opposite of black holes. While a black hole pulls everything inward, a white hole would expel everything outward. Some mathematical models imply that the interior of a black hole might connect to a white hole in another universe. In this view, the matter falling into a black hole does not disappear, but reappears elsewhere, emerging through a white hole in a different space-time realm. But do such universes actually exist? The answer remains uncertain. Multiverse theories propose that our universe is just one of many, each with its own physical laws and properties. If black holes connect universes, they might serve as gateways between them. Some scientists even speculate that each black hole could give birth to a new universe. According to this idea, the singularity represents a cosmic seed, and the burst of expansion inside a new universe mirrors the Big Bang. Still, these ideas remain purely theoretical. We cannot observe what lies inside a black hole. The event horizon blocks all information. We cannot send probes inside or receive signals back. Our understanding of what happens within is based entirely on equations, not observations. Until we discover a working theory of quantum gravity, one that merges general relativity with quantum mechanics, we cannot know whether these possibilities are real. The idea of black holes as portals invites a deeper, philosophical reflection. It reminds us that the universe is far stranger than we can imagine. Even if black holes do not literally open pathways to other universes, they stretch our understanding of reality. They show that space and time are fluid, that boundaries can shift, and that the unknown still lies at the edges of our theories. In the end, whether black holes are portals or not, the question itself pushes science forward. It inspires new models, new experiments, and new ways of thinking about the cosmos. The possibility remains open, not proven, not disproven, but waiting in the darkness beyond the event horizon, challenging us to look deeper into the nature of reality. Time behaves strangely near a black hole. It slows, stretches, and bends in ways that challenge our deepest assumptions about reality. The closer an object approaches a black hole's event horizon, the more dramatically its experience of time diverges from that of an observer far away. At the extreme edge of a black hole, time as we understand it begins to lose meaning. This is what scientists sometimes call the end of time, not in a mystical sense, but in a physical one, where time itself becomes distorted beyond recognition. To understand why time changes, we turn to general relativity. According to Einstein, gravity is not a force, but the curvature of space-time. The stronger the gravitational pull, the more space-time bends. This bending affects not only the motion of objects, but also the flow of time. Near a black hole, gravity becomes so intense that time slows dramatically. This effect is known as gravitational time dilation. Imagine two observers, one floating safely far from the black hole, and another slowly drifting toward it. From the perspective of the distant observer, time near the event horizon seems to crawl. The falling observer's movements appear slower, and slower. Their heartbeat, their speech, even the light they emit becomes stretched into longer wavelengths. Eventually, as the falling observer reaches the event horizon, they appear frozen in place. Their last moment is suspended forever. But this is only half of the story. From the perspective of the falling observer, time feels normal. Their heartbeat continues at the same rhythm. They do not feel time slowing. Instead, they see the universe outside speeding up. Distant stars appear to accelerate. Light from the outside shifts to brighter frequencies. Time outside rushes into the future. In the final moments before crossing the event horizon, its entire future might appear to collapse into a single instant. This divergence shows that time is not absolute. It is not a universal clock ticking the same for everyone. Time flows differently depending on where you are and how strong the gravity is. Near a black hole, time becomes a dynamic, flexible dimension that responds to mass and energy. Inside the event horizon, time changes even more dramatically. The direction of time becomes aligned with the direction of the fall. Once the observer crosses the horizon, moving toward the singularity becomes as inevitable as moving forward in time. Every possible path leads inward. No force, no decision, no energy can change the direction. Time itself becomes a slope sliding toward the singularity. At the singularity, where space-time curvature becomes infinite, our equations fail. Here, time and space lose their conventional meanings. Our models cannot describe what happens, whether time ends, collapses, or transforms into something new. The singularity is not simply a place where matter is crushed. It is a moment in time where the future ends. The falling observer cannot avoid this moment, just as they cannot avoid tomorrow. The singularity lies in their future as inevitably as sunrise lies in ours. This raises deep philosophical questions. If time ends at the singularity, what does that mean for causality, the idea that causes precede effects? What does it mean for the continuity of consciousness? Does an experience have a final moment if time itself dissolves? These questions are not merely abstract. They point to the limits of scientific understanding. In many ways, approaching a black hole represents approaching the edges of our conceptual map. Just as ancient explorers reached the horizon and wondered what lay beyond, physicists reach the horizon of space-time and confront the unknown. Time, which seems so familiar and constant in daily life, becomes fluid and fragile under extreme gravity. Some theories propose that quantum effects might prevent time from truly ending. Instead of a singularity, there may be a region where space-time becomes foamy or granular, governed by quantum rules. In this view, time might loop, branch, or merge with other regions of space-time. The singularity might not be an ending, but a transition. Regardless of the true answer, the study of time near a black hole reveals the universe's profound complexity. It shows that time is not a background stage on which events unfold, but an active, dynamic part of the cosmos, shaped by gravity, bent by mass, and transformed by the universe's most extreme environments. Near a black hole, time does not simply tick. It warps, stretches, and ultimately reaches its limit, reminding us that even the flow of time is part of the cosmic mystery.
Black holes teach us about infinity not just as a mathematical concept, but as a physical reality woven into the universe. They reveal that infinity is not a number, but a boundary where our understanding breaks down, a horizon where familiar rules stop working. In the presence of a black hole, infinity becomes something we can almost touch. Infinite density, infinite curvature, infinite time dilation. Each of these shows us a different face of the cosmos, a quiet reminder that the universe is far larger, stranger, and deeper than anything we can imagine. The singularity at the center of a black hole is the most direct encounter with infinity. According to general relativity, all the mass of a collapsing star is squeezed into a single point zero volume and infinite density. This is not just a large number. It is a point where gravity becomes infinitely strong and space-time curves infinitely sharply. At such a point, our equations cannot describe what happens. Infinity becomes a marker, a sign that our theories have reached their limit. It tells us, beyond this, you do not yet understand. Infinity also appears in the behavior of time. Near a black hole, time slows to such extremes that, from the perspective of a distant observer, an infalling object seems to approach the event horizon endlessly. They never see it cross. For them, time stretches toward infinity, an eternal pause at the edge of darkness. This does not mean time truly stops for the falling object, but it reveals that time itself is not absolute. It can expand and stretch depending on gravity, hinting at a universe where time's boundaries are flexible, not fixed. Space, too, encounters infinity. The geometry around a black hole becomes so curved that distances behave differently. Light can orbit the black hole in a loop, endlessly circling in what is called the photon sphere. Gravity bends the paths of photons so drastically that they can trace infinite paths around the black hole before escaping or being captured. Even the fabric of space-time seems to wrap around itself, creating a region where direction loses meaning. Infinity also appears in the lifetime of black holes. Hawking radiation predicts that black holes evaporate, but the timescales involved are unimaginably long. For supermassive black holes, their lifetimes exceed 100 years, a number so vast that it transcends comprehension. Time stretches to cosmological infinity, a future where stars are gone, galaxies dispersed, and only black holes remain slowly shrinking in a universe that has grown silent. Yet black holes also teach us that infinity can be deceptive. Many infinities in physics are warnings, not literal truths. When equations predict infinity, it often means something deeper is missing, a new layer of physics waiting to be discovered. For example, quantum mechanics may prevent true infinities from forming, replacing the singularity with a finite but extremely dense structure. Infinity, in this sense, is not a physical entity, but a placeholder for the unknown. Philosophically, black holes invite us to confront the idea of limits. They show that even the most fundamental concepts, space, time, energy, have boundaries where intuition fails. They remind us that reality does not conform to our expectations, and that the universe contains realms beyond direct observation. The event horizon itself is a metaphor for knowledge, a boundary we cannot cross, beyond which lies mystery. Black holes also reveal that infinity is part of the cosmic cycle. Matter falls in, compressed toward infinite density, and information is stretched toward infinite time. But through Hawking radiation, even black holes eventually release their energy back to the universe, closing an infinite loop. In cosmic terms, infinity is both an ending and a beginning, a process that shapes the long-term evolution of the universe. Most importantly, black holes teach us humility. They show that the universe is larger and more complex than our current theories can grasp. They invite us to question, to explore, and to accept that some mysteries are not failures of understanding but gateways to deeper insight. In the darkness around a black hole, infinity is not an abstract idea, it is a lived reality, expressed in gravity, time, and space. Through their silent presence, black holes whisper that the universe is vast beyond measure and that our journey toward understanding has only just begun.